Let's start. This is our new topic, linear programming. Where do you see that? This is a mathematical technique. This is a mathematical technique. This is a mathematical technique used to determine. This is a mathematical technique used to determine how well scarce resources can be utilized. How well scarce resources can be utilized. How well scarce resources can be utilized in order to generate the maximum returns. In order to generate the maximum return. In order to generate the maximum returns. In order to generate the maximum returns. Full stop. Good. So now let's look at application of linear programming in business. Applications of linear programming in business. Application of linear programming in business. Number one, in product mix decision. Product mix decision. Number two, inventory controls. Inventory controls. Inventory controls. And number three, CVP analysis. CVP analysis. CVP analysis. Another one, capital budgeting. Capital budgeting. Capital budgeting. Another one, project and network analysis. Project and network analysis. Project and network analysis. Strategy formulation stroke game theory. Strategy formulations. Strategy formulation stroke game theories. Stroke game theories. Stroke game theories. Yeah, those are some of the application in the of linear programming. Now let's look at assumptions. Stroke characteristics. Stroke limitation of linear programming. Assumptions, stroke characteristics, stroke limitation. Yeah, most of the assumption, they are limitation, because assumption means that it just assumes. That means it's not always the reality. So that's why most of the limitation, assumption, are the same as limitations. So limitation, assumption of linear programming. Number one, linearity. Linearity. Linear. Yeah, linearity. What do we mean by linearity? Now we explain. Say that. This rules that there is no economies of scale and diseconomies of scale. This assumes that there is no economies of scale and diseconomies of scale. Number two, proportionality. Proportionality. Can you explain that? The quantity of resources used. The quantity of resources used are directly proportional. The quantity of resources used are directly proportional to the units produced. Number three, divisibility. Explain that. The quantity of resource of a resource, the quantity of a resource, can be divided into smaller proportion, can be divided into smaller proportion. Number 4, additivity. 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 Then let me say that. Various proportions of a resource, various proportion of a resource used by different products, can be added together, Various proportion of a resource used by different products can be added together. Number 5, certainty. Number 5, we have is certainty. All the items involved in the program, all the items involved in the program has a single value expectation. All the items involved in the program have a single value expectation. Yeah, that means we expect the same outcome. That we say that we are certain. They have a single value expectation. Number 6, non-negativity. Non-negativity. See that? This assumes that all the values in the program, all the values in the program are at least equal to 0, i.e., there is no negative value. I.e., there is no negative value. So you can show this, that X should be greater or equal to 0. It cannot be lower than 0. You either produce a 0 unit or you produce more than 0. That's what it means. Then another assumption, number 7, finiteness. All the items involved in the program, are well known and countable, and they are countable, Yeah, those are some of the assumptions or characteristics of limitation of linear programming. Good. So now let's look at methods of linear programming. One, we have the graphical method. And number 2, we have simplex method. You have 2 methods of linear programming. One is the graphical method. The other one is the simplex method. So now let's start with the first one, graphical method. Graphical method. Graphical method. Let me see that. This method, it's applied. This method is applied when there are only 2 products when there are only two products under consideration. When there are only two products, when there are only two products under consideration. When there are two products under consideration. Now let's look at steps forward in linear programming. Steps forward in linear programming. What are some of the steps forward? Now remember that linear programming is a technique used to determine how well scarce resources will be utilized. So that means in linear programming, we are facing some what we call the constraints or the limiting factor. Now in this case, for example, let's assume that to produce certain products, you need 300 labor hours or machine hours. But the maximum you can afford is 280 hours. Now the question is, how can we utilize this to 80? That means we are facing a deficit of 20 hours. Which unit or how many units of a certain product will you produce to achieve your objective? Step number one, determine the objective. You determine the objective, determine the objective. Step number one, you determine the objective. We'll explain, see that? This can either be profit maximization. This can either be profit maximization, or cost minimization, or cost minimization. It's either profit maximization or cost minimization. Full stop. The following equalities are used. The following equalities are used. So, maximization scenario, you use less or equal to. Minimization scenario, we use greater or equal to. Yeah. So the objective is to maximize the profit. You use the inequality of less or equal to. A minimization scenario, you use greater or equal to. So what you need to note that at this level, you'll only be dealing with the cases of maximization. So you won't deal with minimization. Now for minimization, we use a technique known as the transportation assignment or assignment or method technique, of which it's no longer part of your syllabus under this quantitative analysis. So in this case, we'll only be focused with profit maximization. That's step number one. Step number two. Determine the input variables. You determine the input variable. Determine the input variable. You see that? These are variables, stroke products, stroke resources. These are variables, stroke product, stroke resources required to attain the objective. Then step number three, you determine the limiting factor or the constraint. Yeah, or the constraints, or what we call the scarce resources. So you determine the limiting factor, stroke the constraints, stroke scarce resources. Like, let me see that. These are resources which can hinder attainment, the attainment of the objective, Then step number 4, we have non-negativity. Good. We have already discussed what is non-negativity. Now, non-negativity, then you can show this, that x should be greater or equal to 0. That means you cannot produce a negative unit. That's what a negativity assumption means. Good. So those are the 4 steps forward in when solving linear programming. Number 1, you identify the objective, and in this case, you say that we have 2 objectives in a business. It's either profit maximization or cost minimization. But in your case, you'll only be dealing with the maximization cases. Then, and in case you're using the maximization, you'll be using the inequality of less or equal to. Then, once you identify the objective, step number 2, determine the input variable. Now, input variable, what do you need for you to attain this objective? So that's what we call the input variable. Then step number 3, of this input variable in note number 2, what can hinder you from attaining your objective? That's what we call now the limiting factor. So determine the limiting factor. Now, limiting factor is one of these, the input variable, what you need to attain your objective. They are known as the limiting factor or the constraints or the scarce resources. And then lastly, you have to complete with this assumption. You must show that the units you are producing, it's either you produce nothing or more than 0. That means you cannot produce a negative unit. So now let's look at some terminologies. Terminologies. Number 1, optimal solution or optimal corner or optimal point. Optimal solution stroke optimal point or optimal corner. Ready to see that? This is a point whereby the combination of 2 resources, stroke product, the combination of 2 resources stroke product will result to maximum contribution, will result to the maximum contribution. Yeah, this is why the combination of 2 resources or product will result to a maximum contribution. Full stop. Then what we say that? It's the coordinates of the corner, of the feasible region. Full stop. Another point, it's the farthest corner of the feasible region. Yeah, is the farthest corner of the feasible region. Number 2, therefore, let's define what do you mean by feasible region. Feasible region, see that? This is the region containing all possible solutions. This is the region containing all the possible solutions of the problem. Is the region containing all the possible solutions of the problem. Yeah, that's what we call the feasible region. Number 3, binding resources. Binding resources. We explain that. A binding resource is the one which forms the optimal point, is the one which forms, is the one which forms, is the one which forms the optimal point, and they are fully utilized, and they are fully utilized at optimality, and they are fully utilized, and they are fully utilized, and they are fully utilized at optimality, and they are fully utilized at optimality. Number 4, non-binding resources. Non-binding resources. Non-binding resources. So that these are resources which are not fully utilized. These are resources which are not fully utilized at optimality, which are not fully utilized, which are not fully utilized at optimality, which are not fully utilized at optimality. Yeah, we have seen that for binding resources, they are fully utilized. But for non-binding resources, they are not fully utilized. Fully utilized. So that unutilized element is what we call the slack. Number 5, let's define slack. Slack, that's another definition. Slack, what do we mean by slack? See that? This refers to unutilized quantity at optimality. This refers to the unutilized quantity at optimality. This refers to the unutilized quantity at optimality. Full stop. Then you explain, see that? For binding resources, for binding resources, for binding resources, comma, for binding resources, comma, slack is always 0. For binding resources, slack is always 0. Slack is always 0. Now you see, you're saying that slack is that unused quantity at optimality. But you have said that for binding resources, we have those resources which are fully utilized. So that means there is no unused quantity. So that we are saying that for binding resources, slack is always equal to 0. So slack is that unused quantity. This is what I mean. For example, assume that you had 300 machine hours, but of the 300, you only utilized 8 hours. So that means there is a balance of 20 hours. Now, this 20 hours is what we call the slack. And what are the importance of slack? Now, let's below that, you write importance of slack. Importance of slack. Importance of slack. Importance of slack. Number one. They serve as a basis. They serve as a basis of computing resource prices. They serve as a basis of computing. They serve as a basis of computing resource prices. Another importance. Slack can be used for the next production at no extra cost. Can be used for the next production at no extra cost. Full stop. Then we have to see that. Another one, another point. If slack appears, it indicates there is unutilized capacity. It indicates there is unutilized capacity. Yeah, it helps the management to determine that. If they are slack, that means there is some units we are not using or some quantity we are not using. It shows that the company is not operating at a full capacity. Full stop. Good. So now that was slack. Number 6, surplus. Surplus. See that? This is the quantity of a resource. This is the quantity of a resource. This is the quantity of a resource, which is used in excess, which is used in excess, which is used in excess of what was initially available. This is the quantity of a resource which is used in excess of what was initially available, of what was initially available. Yeah, so surplus is what the extra, but this one under profit maximization is difficult to get this. There's no way you can use more than what you had initially. So that means for you to have that additional, that means you have to pay an extra cost. Another definition, number 7. Shadow price stroke overprice. Shadow price stroke overprice. Would I like to say that? This can be defined as follows. This can be defined as follows. This can be defined as follows, semicolon. A, it has 3 definitions. A, maximum price that maximum price paid to acquire an extra unit of a resource. Maximum price paid to acquire an extra unit. Maximum price paid to acquire an extra unit of a resource. To acquire an extra unit of a resource. Good. Number 2. Another definition, that's number B. Maximum profit and for acquiring an extra unit. Maximum profit and for acquiring an extra unit. Maximum profit and for acquiring an extra unit. And lastly, number C, maximum loss suffered for not acquiring an extra unit. Maximum loss suffered for not acquiring an extra unit. Yeah, where do you encounter such a definition? Because that one is a replica of something we had already done. You remember decision making. What do we define? How do we define the value of information? We say that the value of information is the maximum price paid to acquire information, or maximum profit obtained for acquiring information, or maximum loss suffered for not acquiring information. So it's the same as our shadow price. Now, you think that shadow price is the maximum price you can pay for you to acquire an extra unit, or the maximum profit you obtain for acquiring that extra unit, or the maximum loss you can suffer for not acquiring that extra unit. So that's what we call the shadow price. Then below shadow price, you write NB. For non-binding resources, NB for non-binding resources, comma, shadow price is 0. Shadow price is 0. Shadow price is 0. Let me explain that. Let's begin. You see that binding resources, they are resources which are fully utilized. So that means if we had 300, we spend all the 300 hours. Non-binding resources, they are resources which are not fully utilized. So that means there is slack, there is balance. For example, of the 300, we only utilized 280. So there is balance of 20. Now let's come to the shadow price. See that what is shadow price? Now, in case you want to produce an extra unit of this product, you see the binding resources, they are fully utilized. So hakuna kitu imebakia. So that means for you to produce another unit, you have to buy more of these binding resources. What about for non-binding? They are not fully utilized. So in short, tuko na yenye tumebakisha. So that means in this case, for the 20, you will not have to pay again. That's why you're saying that for non-binding resources, shadow price is always equal to 0, because we have unutilized. But for this, binding resources, they are fully utilized. For you to produce an extra unit, you have to acquire more. So now the question is, for you to acquire more, how much will you pay? That's what you call the shadow price. Good. Now let's look at application of shadow price. Application of shadow price. Application of shadow price. How do we, where do we apply the shadow price? Application of shadow price. Yes. If you want that, now that means it will disqualify. If you want that, that means you have to pay for an extra the other 10. Eh? Yes, that one you have to pay amount. Eh? Yes. But in this case, you see, you're saying that it's only cost to produce one extra unit. Yeah, only one extra unit. Yeah. And so now let's look at application of shadow price. Where do you apply shadow price? Number one, in determination of the limiting factor. In determination of limiting factor. In determination of limiting factor. Yeah, that's the first thing. And you know what's a limiting factor? Now, for example, from a student perspective, I was discussing with some other students. They are taking 6 units. They are telling me, I know I'm very committed. So to complete 6 units is very easy. But now the problem is that my schedule is very tight. So that means that student has all the resources. He has the capacity. The only factor is what? Time. Right together. His time is very fixed. So that means in that case, the limiting factor or the constraint to that student is what? The time. Right together. Good. Number 2, sensitivity analysis. Sensitivity analysis. Another application of shadow price is sensitivity analysis. I will discuss that one later. Sensitivity analysis is a test used to determine when one variable is affected, how sensitive is it to the changes in the total profitability. Number 3, they serve as a basis. They serve as a basis of computing resource price. They serve as a basis of computing resource price. They act as a basis of computing resource price. Resource price. Good. That was number 7. Number 8, another definition, multi-optimality. Multi-optimality. What do we mean by multi-optimality? Let me see that. This is where the linear program, not linear programming, this is where the linear program has more than one optimal solution, generating the same contribution, And that's what we call multi-optimality. Remember, you see that it's all about optimal solution or optimal corner. Now, in this case, we're saying that we have more than one optimal corner. That's what we call a multi-optimality. Another terminology, infeasibility. Infeasibility. Yeah, infeasibility is the opposite of feasibility. See that feasible region, this is where we contain all the solutions to our problem. Now, infeasibility, this is where there is no feasible region. So you write that. Infeasibility, you see that? This means lack of feasible region. This means lack of feasible region. We'll stop. Then we explain that. It's brought about by presence. It's brought about by presence of mixed constraints. It's brought about by the presence of mixed constraints. Number 10, unboundedness. We'll explain, see that? This is where the feasible region, this is where the feasible region is not bounded from above. This is where the feasible region, this is where the feasible region is not bounded from above. It's not bounded from above. It's not bounded from above. Also, it occurs when the objective is to maximize. It occurs when the objective is to maximize, but the constraints are in plenty. 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 Yeah, that means this one occurs. If I give you the same scenario I was giving you about the student. Now, in this case, the student has the capability of doing all the 6 papers. But now, the constraint is a period. But now, the exam period has been extended, maybe to the end of the year. So that means what he had termed as a limiting factor, now you have time. You have maybe an additional 6 months. So that's what we call unboundedness. Another one, number 11, degeneracy. 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 Now, to degenerate, that means to disappear. When you say that I am degenerating, so that means you are telling other students, me, I'm just going, you are disappearing. Right? We say that? This refers to the disappearance. This refers to the disappearance of one. This refers to the disappearance of one of the items, disappearance of one of the items from the original program. This refers to the disappearance of one of the items. This refers to the disappearance of one of the items from the original program, in the course of solving the 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 program. Lastly, another definition, reduced value. Reduced value. Reduced value. What do we mean by reduced value? Yeah, we see that. This is the amount by which profit will increase. This is the amount by which profit will increase. Profit will increase if an extra unit is produced. This is the amount by which profit will increase. Profit will increase if an extra unit is produced. 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 Then let's just combine them here. Number 13. Number 13. What do we mean by value? Value, we define value. Yeah. That. This means units produced. This means units produced. This means units produced. Yeah, for linear programming, because we'll come to look at what we call, sometimes you can do linear programming using a software. Now, those software will have some terminology such as value. If you see value, value means the units produced. Another one, number 14, objective coefficient. Objective coefficient. So that this means profit or contribution. This means profit. This means profit or contribution. This means profit. This means profit or contribution. Profit or contribution. And then number 15, after we have right hand side ranges. Right-hand side ranges. So that this means constraints stroke limiting factor. This means constraints. This means constraints stroke limiting factor. Stroke the limiting factor. Good. So I want us to do an illustration. Do an illustration from our question paper. So open with me handout page 9. Handout page 9. Handout page 9. Hoping we are there. Quick limited. Now, before you do that question, let me take you back to the definition of graphical method. Now, under graphical method, we see that this is applicable. We have two methods of linear programming. One was linear graphical method. The second one is the simplex method. We see that under graphical method, this one is applied when we have two products and analysis. Yeah, because you know a graph has two axes. One is the x-axis, the other one is y-axis. So that's why for graphical method, you only use when evaluating only two products. Now, one product will be plotted on x-axis, the other product on y-axis. And how do we solve this? Number one is start by formulation. How do we formulate? Now, let's go back to the steps in linear programming. Steps in linear programming. Number one, we say that you identify the objective. Once you identify the objective, step number two, you determine the input variable. Once you have the input variable, then you identify the limiting factor. And then lastly is the non-negativity. Good. So now let's do that question. You're told that Quick Limited manufactures two products, X and Y, using two machines, B1 and B2. For each machine, there is a maximum of 200 machine hours available each week. There is a maximum of 200. Now, that's one of the limiting factors. If we have a maximum of 200, that means we cannot exceed that 200 hours available each week, and a maximum of 400 labor hours. Also means that labor hours is another limiting factor because you are given the maximum amount we have. So we cannot exceed that. And a maximum of 400 labor hours are dedicated to the production of product X and Y each week. The resource usage per unit in each product is shown in the table below. So you have the resources usage per unit for product X and Y. We have then machine B1 in hours, machine B2 in hours, then we have labor hours. So that means in this case, we have three variables: machine B1, machine B2, and labor hours. And then all of them, they are also limiting factor because we are told that for each machine, there is a maximum of 200, so we cannot exceed. For labor hours, we have a maximum of 400, so it's another limiting factor. Then you are given contribution per unit. Contribution is the same as the profit or the selling price minus variable cost. So if you're given the profit, that means our objective is profit maximization. Required. Formulate the linear programming model to solve the above problem. Formulation. How do we formulate? So here I need maximum attention. Formulation. Now this is how we formulate. We follow the steps. Number one, you start with what we call the objective function. And this is how we formulate the objective function. We say that in our level, you'll only be doing our profit maximization. So you'll say that the objective is to maximize profit, of which will now be denoted by Z. Maximize Z, that means you're maximizing the profit. And then you are given the contribution. Each unit of product X, the contribution is 300. So it's 3,000 of product X plus for each unit of Y, the contribution is 2,000. 2,000 of Y. So that's what we call the objective function. That for every unit of X you produce, the contribution will be 300. For each unit of Y you produce, the contribution will be 2,000. So now the question is, how many units of X and Y will you produce for you to maximize or to obtain the maximum profit? So that's the first step of formulation, objective function. But now, for you to achieve this, you are facing some limiting factor. Then you say subject to. Subject to. Now you show the limiting factor. And we have the limiting factor. Number one, we have machine B1. We also have machine B2. Then we have labor hours. So let's start with machine B1. Machine B1, you require 2 hours to make each product of X and 3 hours to make each product of Y. So you see that it's 2 of X plus 3 of Y less or equal to. We see that when the objective is to maximize, can you go back under the first step? Was objective function. So for objective function, you see that if the objective is to maximize, you use less or equal to inequalities. We do the same for machine B. 4 of X plus 2 of Y should be less or equal to labor hours. It's 5 of X plus 3 of Y should be less or equal to. Let's go back to the first paragraph, the second sentence. For each machine, we have 2 machines. There is a maximum of 200 machine hours. For machine B1 and B2, we have a maximum of 2. So what does it mean? It's either you spend all the 2 or less than 2. Should not exceed that. And a maximum of 400 labor hours. For labor hours, we have a maximum of 400. Then the last step was what? Last step in linear programming was non-negativity. Yeah, non-negativity, now you show them that product X, comma, and Y. If you produce, it should be greater or equal to 0. There is no negative. Yeah, this one you just show like this. X, comma, Y should be greater or equal to 0. That's what you call non-negativity. That's how you get your 5 marks. That's how you formulate. You start with the objective function, then subject to. For you to attain this, remember you are facing some constraints, subject to, and then you show that for the units you're producing, you either produce nothing or greater than 0. Good. Number B. Graphically, solve the linear programming model formulated in 1 above. Graphically, we solve this. Now, if I take you back to the definition of linear programming, you see that linear programming is a mathematical technique used to determine how well scarce resources can be utilized to obtain maximum profit. Machine B1, we have 200 hours. 200 hours, 400 hours. Now the question is, using what we have, how many units of X will we produce? How many units of Y will you produce to obtain the maximum profit? Now that's what we call solving graphically. So number B, solving graphically. So in this case, now we want to determine the number of units of X to produce and Y to produce. How do you formulate this? Now let's be here. You change the inequalities to equalities. You change the inequalities to equalities. This is what I mean. You take the resources. We have the limiting factor, B1, B2, B3. We start with B1. For example, for machine B1, the equation is 2X plus 3Y. Now you change the inequality to equalities. Now instead of saying it's less or equal to, you say that is equals to 200. Then you substitute X, Y, and this I substitute. If X is 0, if now you produce 0 unit of X, how much will it be Y? you get 66.67. What if now you produce 0? Assume that y is 0. You produce 0 unit of y. How much would be x? It should be 100. Good. So that's machine B1. Now we do the same for machine B2. Machine B2, this was the equation. 4x plus 2y. You change the inequality to equalities, is equals to 200. So how do we change that? So here we have x, y. When x is 0, y will be 100. When y is 0, x will be 50. And then we have labor hours. Labor hours. Now, labor hours, the equation is 5x plus 3y is equals to 400. X, y. Assuming x is 0, how much would be y? 400 divided by 3, you get 130? 133.3. Assuming y is 0, if y is 0, how much would be x? 400 divided by 5, you get an amount of 80. Good. Then from there, now we can come up with a graph. So this is x-axis, you have to show that. And this is y-axis, here we have 0. For x-axis, here we brought product x. For y-axis, product y. Remember, you're producing two products, x and y. Then let's look at this. The maximum we have is 133. So we need to come up with a scale. The maximum scale should be 133. So we can have 20, 40, 60, 80, 100, 120, 140. So this one will be 20, 40, 60, 80. We have 100. I have 120, we have 140. The same here, 20, 40, 60, 80, 100, 120, 140. Now we brought. Now let's start with the machine B1. When x is 0, y is 66.7. When x is 0, y is 66.7. That is 7. 66.7 is approximately there. When x is 100, y is 0. When x is 100, y is 0. So then you join that. And then remember the inequality was less or equal to. So should be less or equal to. We should not exceed. So you shade the unwanted part. And this was 2x plus 3y is equals to 200. Machine B2, we do the same. When x is 0, y is 100. When x is 0, y is 100. When x is 50, y is 0. When x is 50, 50 is approximately there, y is 0, so it's there. Then you join that. And then should be less or equal to. So should not be greater than. So you shade the unwanted part. And this was 4x plus 2y is equals to 200. Lastly, we have labor hours. When x is 0, y is 133.3. When x is 0, y is 133.3, so it's approximately there. When x is 80, y is 0. When x is 80, 80 is there, y is 0. Then you join that. Like that. Then you always shade on your right-hand side. That's the unwanted part. And this was 5x plus 3y equals to 400. So now with that, now I want to explain all the definition we had defined. Now, you see now the unshaded part. This is the wanted part. Now, this is what now we call the feasible region. And you see that feasible region is the region which contains all the solutions to your problems. And in this region, we have 3 corners. Which corners can you see? We have this corner A. Also, you have another corner here, the meeting point between the two, corner B and corner C. We also have corner C, but this one you don't count it because the coordinate is 0, 0. So if you take corner 0, 0, that means that you produce nothing of X, you produce nothing of Y. It's like you are telling them, don't do that project. So in this case, we don't consider that. So we have corner A, corner B, corner C. Now the question is, first of all, let's go to the first definition. Let's go to the definition. The first one was the optimal solution or optimal corner. We say that, what is optimal corner or optimal solution? This is a point whereby the combination of 2 products will result to a maximum return. And then you also said that it's what? Yes? Is the coordinates of the, sorry? Is the coordinates of the? Yes, is the coordinates of the corner of the feasible region. Then there's another point you also read. You see that it's is the farthest corner from from what? Where is the farthest corner? Okay, I want you to change that. Is the farthest corner from the origin? Is the farthest corner from the origin? Is the farthest corner from the origin? Is the farthest corner from the origin. So now here we have corner A, we have corner B, we have corner C. So now we want to determine of this feasible region, where is our optimal corner? Is it corner A? Is it corner B? Is it corner C? And the optimal corner is the corner whereby the combination of the two will give you the maximum profit. Then I give you another hint that the optimal corner is the farthest corner from the origin. Now, just using your naked eyes, between corner A, B, and C, which one is the farthest? Using your naked eye from the origin, which one do you think is the farthest? Hey, can someone assist me with a big ruler? There's no big ruler, eh? Yeah. So now let's look from here. If you're moving from the origin, 90% or 180, the farthest corner will be the last corner to be touched. I look for a ruler. So if you're moving from the origin here, the last corner to be touched by this ruler will be the optimal corner. Which one is the optimal point? Which one is the optimal point? Yeah. So that one will be corner B. So, or alternatively, you can just check. give me the coordinate. In case you cannot be able to use your naked eye, there is another way you can do it, the wrong way. So give me the coordinate of corner A is 0, 66.7. Then we have corner B. Then first of all, let's go to corner C. Corner C, this was 50, 0. 50, 0. So how do you get for corner B? Let me show you how to get for corner B. In case you are not sure, this is what you do for corner B. Coordinates of corner B. So this corner B is made up of two equations. We have 4x plus 2y plus 200. And then it's also made up by this equation where we have 2x plus 3y is equals to 200. Then you solve simultaneously. So here you multiply by 1, here you multiply by 2. So this one will be 4x plus 2y is equals to 200. I'll have 4x plus 6y is equals to 400. Then you minus 400 minus 200, you get 200. 6 minus 2, you get 4y. That means y is equals to 50. If y is 50, you get x. You substitute. Y is 50. 2 times 50 is 100. Take it to the other side. 200 minus 100, you get 100. 100 divided by 4, you get 25. So that means corner B, x is 25, and this is 50. So you want to determine of the 3 points, which one is the optimal corner. The optimal point is a point whereby it will result to a maximum profit. Now, these are objective functions. For each unit of x you produce, it will give you 3,000. Each unit of y, 2,000. So the first one will be 3,000 for each unit of x. X is 0. For each unit of y, the profit is 2,000. So it's 2,000 of y. In this case, our y coordinate is 66.7. We do the same here. 3,000 for each unit of x. X is 25. And here we have is 2,000. And here 50. 3,000 for each unit of x, of which we have 50. And then here you have 2,000. Here you produce 0. So this is 150,000. This one is, the second one is 175. 133, 400. Which one is giving you the maximum profit? 175. So that means the optimal corner is corner B. This is the optimal corner. So the optimal point is where x, you produce 25 units, and then y, you produce 50 units. That combination is the one that will give you the maximum profit of 175. Good. So meanwhile, you can copy that before you answer the other one. So now let's be here. So I want us now I try to interpret to you on various definitions. That's the SRAC, the shadow price, all that, on what it entails. Want us to come up with a schedule like this. So we have the resources. Don't copy, let me explain. Resources, we have machine B1. We have machine B2. We have the labor hours. Then we get their status. Status means that whether they are binding or non-binding. Then also we determine the SRAC as well as the shadow price. So go back to your definition. Let's go back to the definition. Now we want to determine the status of these three resources. Now we start with the binding resources. So what's the binding resources? We see that these are resources. Yeah. So we are saying that binding resources, they are resources which are fully utilized and they make the optimal corner. This is why you have the optimal corner. Now, the resources that makes this optimal corner are known as the binding resources. So number one, you had 4x plus 2y, 4x plus 2y. That was machine B2. Machine B2, that means the binding resource. Also, this corner, it's made up by this equation, 2x plus 3y. 2x plus 3y is this equation. So machine B1, it's also a binding resource. Labor hours does not make the optimal corner. So therefore it becomes an unbinding. Good. So that means the resources that makes this optimal corner are one that we call the binding resources. Then you determine the SRAC. We say that what is SRAC? So SRAC is the unused quantity. And we say that if SRAC is unused quantity, binding resources are those resources which are fully utilized. So if they are fully utilized, there is no SRAC, but we have an unbinding. So let's determine the SRAC. Say that SRAC is the unused quantity at optimality. For labor hours is non-binding. Labor hours, we had a maximum of 400 hours. Now, of the 400 hours, how much did we use? How much did we interest? I use this equation for labor hours. You need 5 hours to make each unit of X, 5 hours to make unit of X. At optimality, we produce 25 units of X. Plus, to make each unit of Y, you require 3 hours. So it's 3 of Y, of which Y we have, it's 50. So that means it's 5 times 25. This is 125. This is 150. That's 275. So you trace 275. Of the 275, we had 400. So that means how much do we not utilize? 125. Good. Even if you try to compute for the two, you'll get a 0. For example, let's take for machine B1, it's a binding. Binding is 200. We minus 2 units, 2 hours to make each unit of X. How many units of X did you produce? 25 times 2 get? Each unit of Y you require 3 hours. 3 times Y. How many units of Y did we produce? 50. 50 times 3? 150 plus 50 you get? 200 minus 200 you get? 0. Good. And then lastly, we look at the shadow price. What is shadow price? This is the profit increase if we produce an extra unit, or the maximum price paid to acquire an extra unit, or maximum loss suffered for acquiring an extra unit. And we said that I gave you an NB and a shadow price. Can you go back where you define the shadow price? There's something we read to say that for an unbinding SRAC is shadow price always equal to This is 0. Because for you to produce, we already have a neutralized. So to make another unit, you don't have to buy. But for the 2, we already have 0. So for you to produce an extra unit, you have to buy more. So now the question is, how much more will you pay for you to acquire that? Or how much profit will you get for acquiring or for producing an extra unit? So now we compute the shadow price. And we compute the shadow price for the binding resources, the 2. Machine B1, machine B2. Here is machine B1. Machine B1 was 2x plus 3y is equals to 200. Machine B2 is 4x plus 2y is equals to 200. Now let's start with, this is machine B1. This is machine B2. We want to determine their shadow price. So now let's start with B1. B1. We see that what is shadow price is the maximum price paid to acquire an extra unit. So here we had 200 for B1. So now it will be 2x plus 3y. Of the 200, if we acquire an extra one, it will be 201. Then you don't change for B2. Remember, you're evaluating B1. So you take 4x plus 2y is equals to 200. Then you solve simultaneously. You multiply by 2, you multiply by 1. This one will be 4x plus 6y is equals to 402. You multiply by 1. 4x plus 2y is equals to 200. So here you'll get an amount of 202. This is 4y. Give me y. To get 50.5. Now let's get x. Now, when substituting for x, you only substitute the one you added 1. Remember, you're evaluating B1. Don't substitute to this. You substitute the first one, the one you increase by 1. So in this case, y is 50.5. So you take 50.5 times 3. Then you take 201 minus answer. Then you divide by 2. So you substitute the first one, the one you added 1. Substitute for x. You get 24.75. Now, how much will be our new profit now? So our new profit, this is what I mean. For each unit of x, the profit is 3,000. For each unit of y is 2,000. So it will be 3,000 for each unit of x. Now, in our new scenario, our x will be 24.75. For each unit of y is 2,000. So it's 2,000 for each unit of y. In this case, our y is 50.5. How much would be a new profit? 175? 250. And how much was the optimal profit at optimality? Yeah, optimal profit at optimality for corner B was an amount of 175. So that means, you see, this is profit. If we produce an extra unit, of, you acquire an extra resource of machine B1, profit will increase by how much? Profit will increase by 250. So here you get 250. You didn't understand that, understand for machine B2. So now let's do for machine B2. We follow the same process. Machine B1 is 2x plus 3y is equals to 200. Machine B2, it's 4x plus 2y is equals to 200. But now you're evaluating B2. What if we acquire an extra unit? Initially, it was 200. If we acquire an extra unit, now it will be 201. Then you solve simultaneously. You multiply by 2, you multiply by 1. So this one will be 2 times 2, you get 4x plus 6y is equals to 400. This one will be 4x plus 2y is equals to 201. So simultaneously minus, this one will be 199 is equals to 4y. Give me y. 49.75. Now let's get x. Now we substitute, but we only substitute to the equation the one we added 1, not the first one, but the one we added 1. So now if y is 49.75, you multiply by 2, then 201 minus answer, you divide by 4. You get? Sorry? 50.75. What are we getting? 0.375. So now let's get our new profit. Our new profit will be, for every unit of X, the contribution is 3,000. So it's 3,000 for each unit of X. So our X is 25.375 plus, for each unit of Y is 2,000 for each unit of Y. Our Y is 49.75. How much will be a new profit? 175,625. Then you compare the new profit against our optimal profit. Now, our optimal profit after optimality was an amount of 175. So how much will be the increase in profit? Profit increase have increased by an amount of 625. Good. Yeah, that's what we call the shadow price. And sometimes you may get a negative. If you get a negative, still will be your shadow price. You see that it's also the maximum loss suffered. Maximum loss suffered. Now let's go back to the required. Go back to the required. Required number 1, we're in handout page 9. Number 1 was formulate the linear programming model to solve the above problem. You already formulated. B, graphically solve the linear programming model formulated in 1 above. Now, graphically is up to this point where you obtain the optimal point. The number of units of X and Y to produce. You're done with that. You get your 5 marks. Number C, compute the shadow price for each constraint. Shadow price. Even they didn't want slack. You have already computed the shadow price. You get 6 marks. And then number D, interpret the meaning of the shadow price obtained in 3 above. You interpret them. I think I've explained. In short, the examiner was trying to test you. Do you know what is shadow price? So this is the profit increase if you produce an extra unit. This is profit increase if you produce an extra unit. And this one, it won't change. Good. So in short, they are testing. Do you know what we mean by the shadow price? So you can copy. And then your next session, you'll do more question in linear programming. Now here I have a question. When labeling the graphs with the equation, do we use the inequality sign? No. Now in this case, yeah, for example, this one is 5x plus 3y. Just write it equals 2. You see, we see that when solving graphically, you need to change the inequalities to equalities. So in this case, this is part of solving graphically. So you don't work with the inequalities, we work with the equalities. You change this sign of inequality to equalities. So it's okay the way it is. 5x plus 3y is equals to 400. Don't write less or equal to. Because less or equal to has already been represented by the shading. Remember, your only concern should be less than. So you shaded the unwanted part. I hope now that's clear.